כן, אז קודם כל תודה לכל מי שהגיע, אנחנו עכשיו קהל די גדול. אז היום איתנו פה הילה, שהיא יונית, שנראה לי שגם על הקו עשתה את הקישור, והיה עובד מייקרוסופט לשעבר, אז עבר לא מזמן לטובת הדוקטורט. זהו, ניתן לך מפה לקחת את זה.
תודה רבה. There are two people that prefer English on the chat, I think.
Oh, some people said that they prefer English?
Yeah, it would be better if it's in English, right? So,
okay, so I saw that there were a few non-Hebrew speaking people that signed up for this lecture. This lecture was intended to be in Hebrew, but we'll do it in English, and hopefully if you have any questions, you can ask them in Hebrew if you feel more comfortable, and I'll do my best to accommodate all your questions. By the way, I just wanted to say we're living in crazy COVID times, so I don't see any of you actually. It would be much easier and more pleasurable, I think, for all of us if you ask questions. I would prefer that this would be, a discussion between me and you rather than me speaking to myself and to Moshe, which is kind of weird. So feel free to ask questions, and I would really love to answer any question that you may have on what I'm saying. So that's it. Okay, so a bit about me before I start speaking. I'm Hila, as Moshe introduced me. My bachelor's is from the Technion in computer science. I'm a PhD candidate at Tel-Aviv University under the supervision of Professor Lior Wolf. My focus in my research is attention-based models, obviously, for computer vision, NLP, and cross-model tasks, which is one of my favorite fields to research. And as Moshe mentioned, I'm a former research intern at Microsoft's Innovation Lab here in Israel.
You can look at this screen.
Oh, look at this screen? Oh, okay. Sorry about that. So what are we going to see today in this lecture? First, we're going to see an intro, okay? I'm not assuming any previous knowledge on transformers or on attention, but I am assuming that you are familiar with basic concepts of deep learning, machine learning, etc. So we look at in intro to transformers, how the model was born and what are the motivations. Then we'll deep dive into the attention mechanism, since this is going to be the main issue that our lecture is going to talk about. Then we're going to look at transformer explainability, why it's interesting, state-of-the-art methods, and then we're going to see examples and use cases, which will hopefully be cool and will stir your interest in the field. Okay, so where did we begin with transformers? Transformers came from natural language processing. So in the beginning, we had RNNs. RNNs are recurrent neural networks. Why recurrent? Because you have the same computational mechanism working again and again, one timestamp after the other. So basically, an RNN at each timestamp gets a token from the text that we are processing and outputs a hidden state. So say we have a sentence like the cat sat on the mat. First, the RNN will process the word the, and then the word cat, and then sat, on, and the mat. So it is sequential by definition. It takes at each timestamp an input token, it processes it, and outputs a hidden state for all the text that it read up until this point. And this was really the state of the art in NLP up until 2017. So why do we need to change RNNs? Why aren't RNNs enough? So the first motivation is that RNNs are wasteful in training time. As we said, the processing is sequential. We process each token at a time. So in order to get the hidden state for the current token that we're looking at, we had to process all the previous tokens in the input. So it is sequential by definition. There is no parallelism, even though we know the entire sentence, from the beginning. So it is very expensive in time. The second thing is that researchers have shown that for long texts, the influence of faraway input fades with time. As we said, we process each token at a time. So if you imagine a very, very long text, once we get to the end of the text, the hidden state is really focused on what was near the end of the text and not things that were really in the beginning of the text. So there is limited context to this mechanism. due to its, sequential nature. So this is the second issue that we're trying to solve. And the third issue that we're trying to solve is that this processing, is unidirectional by definition. We only look at tokens that came before us. If we're processing language in English, then we're only looking at tokens that were on the left of us and not on the right of us. So each token can only refer to tokens that came beforehand. Okay, so we got our motivation to why RNNs are wasteful and we want to replace them. In 2017, Google releases Attention is All You Need, which really revolutionized, the NLP world and then also vision world. What is new about Attention is All You Need? Because the attention mechanism, for those of you who did NLP, you know that the attention mechanism already existed for RNNs. So what is the new, breakthrough? What is so special about this model? The thing that is so special about this model is that it is pure attention-based. Okay, it has no convolutions, no recurrent units, only attention, which is a very simple mechanism. We'll dive into it later, but this was really, the new word in NLP. Be very simplistic, leave out all the RNNs and convolutions and focus on a very, very simple architecture. So let's take a big high-level look at what a transformer looks like. As you can see, the architecture, although it may seem to be a bit intimidating and large, it is really very simple. Most units that you have here are multi-headed attention, and the other units that you see here are simple feed-forward layers, which are the basic building block of any neural network, and linear layers and residual connections. So this is a very clean, simple architecture that is surprisingly also very expressive and, good at its job. Okay, so let's, take a big overview on what attention does. The encoding is done in parallel. So it is not the RNN that processed each token sequentially and had to process all the previous tokens in order to process the current token. Here, all the processing is done in parallel. So we already have that advantage that we were talking about that RNNs didn't have. But the attention operation, as we'll see, in the next slides, it has no consideration of order. What does that mean? It means that the attention mechanism itself does not know which token came before which other token. And this is very important when we process language. If you take a bag of words, you can, shift them and manipulate them and permute them in several ways to create multiple sentences with different meanings. So this attention mechanism has no knowledge of the order of the words in the original sentence. So what the solution that was proposed is to add positional encoding, which you see over, right near the input, you have positional encoding, which adds to the attention mechanism that knowledge of knowing which token came where. Okay, so let's take a deep dive into the encoder, since it's going to be the main processing unit that this lecture is going to speak about. So as we said, the encoder encodes all the information in parallel. Everything is done at once. So the whole state is updated together and not in a sequential way. The idea of the encoder is that it creates contextual representations, and we will see what contextual representations mean. But just intuitively, what it does is it embeds each token in the sequence such that each token gets information from the other tokens. So say again, we have our classic example, the cat sat on the mat. The word the, which is in the beginning of the sentence, is quite meaningless without context from the word cat, right? Because that can refer to many other words in many other contexts. So what the encoder does is it actually adds information to each token from the other tokens. After the encoding phase, each token will have information from all other tokens in the sentence according to the relevance of the other tokens to the existing token. So say we have, again, the cat sat on the mat. Since we assume that the word cat really influences the word the and the understanding of the word the, we would expect that probably the embedding of the word the after the encoding will contain many of the embedding of the word cat. So really what the encoder does is it creates rich representations for each of the tokens in the input, which is basically, the goal of language models. Language models, what they do is they create representations for each word in the text. So do you have questions until now? Anyone wants to say something?
Yes. How do you train this encoder?
Sorry, could you please repeat? I couldn't hear you.
How do you train this encoder? What's the input?
Right. It depends on the data, right? The task that you're trying to perform. The original paper attention is all you need was trained on translation data, which means that the inputs were text from one language, say English, and the outputs were text from another language, say German. But it really depends, on your task. But we'll look into tasks for training a bit later when we'll speak of BERT. Any other questions?
Yes, for the embedding for each token, do we have a vector embedding or a matrix embedding?
Yeah, each vector is embedded each word is embedded as a vector, or more correctly, each token is embedded as a vector. Yeah. There's a process of tokenization, which I really don't want to get into because, it deviates from the topic of our lecture. We'll mostly look at vision examples, but yes, each token is represented by a vector.
The question is more, the attention mechanism gives a pairwise embedding or one embedding per token?
It gives one embedding per token, and we'll take a deeper look into the attention mechanism and what it does, pretty soon. It's going to be a big topic in our lecture, so we're going to see it pretty closely very soon. Okay?
Thank you. Yeah.
Thank you for the questions. So the decoder is really a part that we're not going to focus very much on in this lecture, but it also has self-attention and encoder-decoder attention. Hi. So let's just look at an example of how the encoder and the decoder look from a very nice blog post, the Illustrated Transformer, which is one of my favorites. So we get an input, say a sentence in French, I think, in this case, and the encoder embeds each word in the sentence in order to contain, as we said, contextualized information from the other tokens. And then the information from the encoder passes on to each decoder layer. So each decoder layer gets both the output up until this point and the encoded information. And then the decoder outputs one token at each timestamp. So the decoder is actually, if you think about it, kind of sequential as well, because it outputs a single token at a timestamp. But as I said, the decoder is really not the focus of this lecture. It's just, a nice overview. And any of you interested in understanding better the flow of the encoding and decoding can read the Illustrated Transformer, which is a very recommended blog post. Okay, so let's deep dive into this amazing magical self-attention mechanism, which is the heart of any transformer-based model. The beauty of self-attention, in my view, is its simplicity, okay? It's based on matrix multiplication, linear projections, and a softmax operation. A very, very simple, very clean mechanism, which magically works very well for many, many tasks across, NLP, vision, and cross-model tasks. So what is this amazing self-attention mechanism? It is based on a very simple intuition that we know from information theory. When we search something in a data set, right, we have a query, the query that we run on the data set, say, select star from, I don't know, people where ID equals 1, right? So the query is the query that we're running, the search query that we're running on our data set. And the data set is mapped by keys and values. So each value is represented by the key. So what the self-attention mechanism does is a very simple operation. Basically, if we want to see which words are relevant to the word the, say, we run a query on the entire input that we have and search the relevance of each word to the word that we're looking for right now. So we have three embedding matrices, WQ, WK, and WV, which embed our input into queries, keys, and values. And then each word searches all the other words for relevant words to add to it. So if we look again at an example from the illustrated transformer, say we have two words, thinking and machines. So each word has its embedding, its vector embedding, x1 and x2. And our WQ, WK, and WV map these embeddings into queries, keys, and values. And then we can calculate the similarity between each pair of words. So the similarity between the word thinking and the word thinking itself is the dot product between the query representing the word thinking and the key representing the word thinking. So basically a dot product similarity between the embeddings of the same word twice. And the similarity between the word thinking and the word machines is the dot product between the key, the query of thinking, and the key of machines. So basically, we took a query for the word thinking, which is Q1, and ran it on the entire data set that we have, in this case, all the words. This dot product represents the similarity between the two words, or how relevant is the word thinking to the word thinking, and how relevant is the word machines to the word thinking. Basically, all we did here is calculate dot products and similarity scores between each pair of words. Any questions about this? Because really this is, the heart of the attention mechanism. Okay, great. So after we've calculated those similarity scores, as I said, we incorporate data from the other words into the current word. So say here we had the word thinking influencing thinking by this factor, and the word machine influences the word thinking by this factor. We'll create a new representation for the word thinking, which incorporates the word thinking using this factor and the word machines using this factor. And in order to create a distribution from these similarity scores, we use softmax. Okay, the softmax operation creates a distribution from these scores. So basically now every token is a linear combination of all the other tokens, where the linear combination is weighted by the relevance of each word. So the word thinking will have a linear combination of the word thinking and the word machines, where each word gets a score by the similarity scores using softmax.
Yes, question.
Yeah, sure. Yeah, sure.
Erez?
Anyone?
No.
Erez? Questions?
Maybe not.
Maybe not.
Oh,
Okay.
sorry. It is an accidental press. I don't know even how I did it.
Okay, that's okay. Okay, so this is a very, very simple mechanism. But as we saw before, it is not simply, self-attention. It is multi-headed self-attention. So why is it multi-headed? And this is also a title from the illustrated transformer, which I really love, the beast with many heads. Why do we need multiple attention heads? The reason is that, as we said, in order to turn these similarity scores into a distribution, we use the softmax operation. The softmax operation really, binarizes your distribution. It will end up being, one or two words having a very, very high score, and all the other words being, flat at scores very near zero. So basically what that means is that each word is going to be influenced by a very sparse amount of other words. So if we don't use multiple heads, basically we'll, contextualize each word by, say, one or two other words, which kind of limits the mechanism. So what we're doing is actually we're splitting it. Instead of doing a single self-attention layer, we're doing multiple self-attention layers. Okay, it's the same layer, but multiple self-attention operation across multiple heads. And intuitively, we're hoping that each head will have different one or two tokens that influence all the other tokens. So this softmax operation really forces us to use multiple attention heads in order to make this mechanism more expressive. Okay, so this is just an overview of everything that we saw. We calculate a similarity score between all the tokens using the queries and the keys matrix. We do the softmax operation in order to create a distribution, and then we create, you know, an embedding that is enriched using the similarity scores. Okay, so why self-attention? Why is it so great and so wonderful? As we said, it allows for a very rich representation because each word can get context from all the other words, right? You're not limited by which direction you're processing the input from, and really it has no meaning, right? Because the attention mechanism simply calculates similarity scores. It has no idea which word came before which, and this is why we also needed the positional encoding. So it allows for a very rich representation, and each token really contains information from limitless amount, you know, of other tokens. So it is a very rich and expressive mechanism. So in comparison to convolutional neural networks, because we're going to speak of vision, you know, very, very soon, the difference between self-attention and convolutions is the inductive bias. When you look at convolutions, they actually do maybe a similar operation where you have a kernel that, you know, is being shifted through the image, but the convolution operation includes an inductive bias. The inductive bias really implies that each pixel is influenced mostly by its neighboring pixels. Okay, so if we look at this image, for example, the 1 in the leftmost corner cannot influence the 0 in the rightmost corner below, due to this inductive bias. So really attention alleviates this bias, right? Because any token can refer to any other token. So it doesn't have that inductive bias that convolutions have for image processing. So if it is so great and so wonderful, why isn't self-attention used anywhere and everywhere? It is quite expensive in space, because if we think of those similarity scores that we've calculated, if we think of a 224 by 224 pixel image, for example, the attention matrix will be 224 by the 4, since we need to calculate similarity scores between each pixel and each other pixel. So it is very expensive in space, but I will say that there is many research around, you know, making this attention mechanism more efficient. So it has caveats, but let's stay tuned for what researchers come up with next. Okay, so after we had, you know, attention is all you need and the birth of the transformer, really what really revolutionized the NLP world, I think, in my opinion, was BERT. BERT was a model that only took the encoder part from the transformer and used it to create, as we said, contextualized embeddings for each of the tokens in the input. So what BERT did was it really introduced self-supervision to transformers, and I think that this is, you know, really the most common approach for using transformers nowadays as well. So what they thought of was, you know, we trained these models for each task from scratch. So if we have, say, a transformer and we want to do sentiment analysis, we'll train it from scratch for sentiment analysis. If we want to do part of speech tagging, we'll train it from scratch for part of speech tagging. But humans don't learn tasks from scratch as if they don't know language at all. We learn the language first, and after we know the language, it is very easy for us to adapt ourselves to various tasks using our understanding, our pre-existing understanding of the language. So what BERT did is said, you know, we have so much data online available out there. Why not use it to train a model that really understands language rather than training a model for each specific task? So what they did, and I think the most influential self-supervision task, which was then replicated for vision transformers, if you know it, it was masked language modeling. What they did was, sorry, it jumped, was take a very long unlabeled text from the internet, and they hid specific tokens from the model, and they asked the model to complete the missing words, the missing tokens. under the assumption that if the model knows how to complete a text in a way that makes sense, that is reasonable, then the model really understands language. So this is the training task. If we were talking about, before about training tasks, this is the training task that the model was trained for, only prediction of missing words. And what they saw is the amazing ability to fine-tune or transfer learn this model into various tasks across NLP. And really BERT, improved the state of the art by a very large margin, without needing the same insane amounts of data that we would usually need to train such a big model, okay? So really it's a new conception of how we see the world. We need to train models that really understand the domain that we're working on, language, vision, etc. And then we will probably need much less data in order to make the models make the transition from what we train them to any task that we want with that domain. So what are the advantages of using self-supervision? No need to design an architecture per task. It's the same architecture for all tasks. No need to produce very large data sets per each task. A small one would suffice, right? If you're working in NLP, you know that biases in Mechanical Turk is one of the biggest issues that we have, because most of the data that we have, either we don't have enough data, or the data that we do have is labeled sometimes, the wrong way or in a biased way. So we don't rely on having tagged data sets for each task. The other thing is that we don't need to sacrifice the expressiveness with inductive biases, because we have so much data online available and free that we don't need to really, add biases to the model and in order to train the model with less data. And so this is really intuitive and nice approach, because it is similar to what we do as humans. Thank you.
Yeah,
we first learn the language, and then we have a very easy time adapting to any task that we're presented with. So this is the concept of self-supervision. And are there any questions at this point? Okay, great. So up until now, we were talking about the attention mechanism as creating a new embedding for each word, but how is classification done? Classification is done using a special classification token, which is not representing any real input, and it is appended usually to the beginning of the text. As you see here, the sentence here is "my dog is cute," and the second sentence, "he likes playing." And in addition to the tokens that describe the input, there is another token that is the classification token. The attention mechanism will embed into the classification token information from the entire text, okay, global information. And then in the end, when we want to do classification, we'll dump all the embeddings and only use the classification token. And this classification token will give us, using a linear layer and softmax or whatever, very simple operation, will give us the classification for the entire text. So this is actually a very important point, because we're going to see how it influences our explainability mechanisms later. Okay, so as we said, BERT really revolutionized NLP, but then, researchers in vision said, we want to have this amazing attention mechanism in vision as well. So not only in NLP, but also in vision, really the transformers have created a real revolution across many tasks, not just classification tasks, also generation tasks. And let's look at the vision transformer. Okay, so now we're making the transition from NLP, which up until 2020 had, the full dibs on all transformer-based networks. And in 2020, Google releases another revolutionary paper called "An Image is Worth 16 by 16 Words." And the transformer is, used for vision as well. And really, the architecture here is very, very simple. We take an image, we divide it into patches. Each patch is projected into a single vector using a linear projection. We add a classification token, as we did in BERT. And we use a simple transformer encoder, so nothing really sophisticated going on here, right? Very, very simple, very clean architecture. That's the entire model, really, here, right here. Question?
In the chat.
In the chat, I can see it. So someone's going to need to read it out loud.
Yeah, I can do it. Doesn't 520 tokens window creates an inductive bias?
Oh, right. So basically what we do have, a limitation that we have is usually the number of tokens that we can process due to, you know, as we said, the limiting space of the self-attention mechanism. So basically, we do have a limitation of the number of tokens that we can process. BERT, for example, has 520 and sometimes 1,024 tokens limitation. I don't know if I want to call it an inductive bias. At the very least, it is a much bigger span or much bigger window that the model can look at than what RNNs had. So maybe let's call it not really an inductive bias, because it's not really a limitation of the model itself. It's a limitation of our computational power, right? If we had infinite computational power, then we would have, you know, a sequence as big as we want and as long as we want. I wouldn't really call it an inductive bias because it's not something that we created inside the architecture itself. It is a limitation that stems from, you know, our use of the model and our computational limitations, if that answers the question.
And there is another question. While it was shown in 2020, sometime after BERT, was there any limiting belief it wouldn't work on vision?
I think it was attempted before the vision transformer, right? Some papers tried to, you know, introduce transformers to vision, but very, you know, in a very limiting way, and it was really not as successful as the vision transformer. I don't know if there was a belief that it wouldn't work so much as there was a belief that it's going to be harder than it is for text, because with an image, you know, 224 pixels is really a small image, 224 by 224. While for text, you know, you can embed each token into a vector, and it's kind of natural. So it was really unclear how we're going to get this to work for images, and also very unclear due to, you know, the limitations of our computational power, how and if we can even do self-supervision for vision transformers. So the original vision transformer didn't do self-supervision. It used a lot of training data with a data set that isn't even public. It is private within, you know, Google. So it used a whole lot of data in order to train a reasonable model. But after it, you know, we had other models such as Date, Clip, Dino, Bait, and so many more who successfully did self-supervision or distillation for vision transformer.
In the previous slide, you showed that the one before, sorry, the NLP task, the positional encoding slide, sorry.
Oh, it is way back, yeah. There is positional encoding here too.
Exactly, but before that, there was a tokenization to the sentence itself, right? So it split the word playing to two parts.
Yeah.
So how it's been done in Vision?
In Vision, basically the image is just split into patches, okay? So for our vision transformer, the basic vision transformer, it's worth 16 by 16 words because usually it's divided into 16 by 16 patches. There are also other variations, but I think this is the most common one. 16 by 16 patches. Each patch is going through linear projection and embedded into a single vector.
And we have one more question, I see. Eyal?
Yes. So the input is an embedding of the patch, or just the patch itself vectorized?
No, it's an embedding. There is a linear layer because each patch here is not, you know, a single vector. It is, you know, an image. So
in NLP you have word to vect and all its variations, and specifically in BERT sentence piece. So what's the similar algorithm in Vision?
A linear layer. A very, very simple linear layer. Okay, you can. It is a very simple mechanism.
But it is self-trained on some task?
No, the linear layer is part of the architecture. It's being trained as part of the vision transformer with all the other transformer layers.
Is it replacing the word to vec?
In some sense, it's replacing the word to vec plus the embedding. You know, you have, yeah, in some sense, it replaces the word to vec. In NLP, what you do is you do a tokenization to the input, and then you have an embedding matrix which maps each token into a vector. So yeah, it's kind of a word to vec. You can think of it as patch to vec. Okay.
Sorry, another question, please. First, if you can go back to that slide. Yes, first, the linear projection is, if first you take the patch and you flatten it, and then you take linear projection?
Yeah.
Or?
You can think of
it No. My question is whether the why am I asking this is to know whether the let's say the vertical spatial information or the vicinity of pixels information is lost in this linear projection, or is it kept somewhere, somehow? You see what I mean? If I just flatten it, then I have the horizontal axis. I have the
it is implemented as a convolution. The implementation is as a convolution with the according to the stride and the kernel size. So you can think of it as a convolution.
Okay.
Yeah. Okay.
So it does maintain this information. Okay, thank you.
Yeah, okay. So just to give you a motivation of what the vision transformer did in the vision world, one of my favorite models, DALL-E from OpenAI, which does text to image generation. And you can see here a very, very complex text prompt, an emoji of a baby penguin wearing a blue hat, red gloves, green shirt, and yellow pants. And the model is actually able to produce images that correspond to that very elaborate and very particular text prompt. And I think that the abilities that the vision transformer introduced to the vision world are insane and unlimited. And just, you know, to give you a small motivation of some of the things that people did after the vision transformer came out. So we actually did another work that isn't on explainability, which is called target clip. This work uses the clip embedding space of the images in order to transfer semantic essence from a target image into a source image. So just to give you another motivation of an amazing model, clip, that uses transformers. Clip uses simple contrastive learning in order to train an image encoder and a text encoder. And really what is special about Clip is since it uses text to measure the similarity between images, then if you look at two images are going to be similar in the Clip embedding space if they are semantically similar, okay? If they have the same semantic qualities. So basically this allows us to transfer the semantic qualities from one image to another, since the clip embedding of an image is mostly based on its semantic properties. So you can see here that we've transferred the semantic qualities from the Joker to Hillary Clinton, from Trump to Obama, from Ed Sheeran to Elon Musk, and Taylor Swift as Avatar, and Doc Brown, if you like, Back to the Future, and so on. So really, you know, the possibilities that transformers introduce into the world of vision also are limitless. Okay, let's dive into explainability. This was supposed to happen 12 minutes ago, but we'll try to catch up. So what is explainability? Explainability is a field of research aimed at revealing what parts of the input determine the model's output. So basically we have these huge models, you know, we're speaking of transformers, millions and billions of parameters worth of models. which do very complicated, tasks such as classification or, as we saw, generation, and we have no idea what these models actually learn. So the explainability research field is a field of study that tries to explain why the model outputs what it outputs. So say here we have the image of the bird, of the parrot, I think. We see here a heat map corresponding to the bird that actually highlights the pixels that correspond to the bird in the image. So we actually can see that the model really relies on the correct pixels in the image in order to make its classification. So deep neural networks are used very widely in our everyday life, even for law enforcement, medicine, social networking, banking, etc. We trust those networks, kind of trust maybe nowadays, but we don't really know what's the logic behind those networks. And as we said, most, transformers, mostly in NLP, are trained on with self-supervision on data from the internet. So some models that have trained on data from the internet have picked up some biases that the internet contains. As we know, the internet is misogynistic and racist. So really properties that we wouldn't want our models to hold. So explainability is aimed at first instilling trust in us, the users, so we know that we can really trust those models that we're using. The second thing is detecting the biases. Say if my sentence was about two Jews walking into a bar and the sentence was classified as negative, in the negative sentiment, you can see that the explainability sometimes matches the bias that the model has. So if the model has a bias that Jews are bad, then the words that are going to correspond to the negative sentiment are going to be the biased words, the Jews, say, for example. So it assists us in detecting the biases of the model and also reveals the logic behind the decision-making process of the model, which is, crucial for us as data scientists, as deep learning researchers. We want to know why our model got something wrong. If it classified a dog as a cat, we'd probably, see the benefit in seeing the pixels in the image that determine the mistaken class. And maybe in that way, we could improve the model from an understanding point of what the model thinks and what it sees. So if we deep dive into transformer explainability, we said that we calculated a similarity token for each two tokens in the input. So what we see here is the attention matrix, right? We have the tokens, the classification token, which we appended, token 1, token 2, token 3, and so on. And we have similarity values that we've calculated using the dot product between the queries and the keys. And as we said, when we do classification with transformers, we dump all the tokens except for the classification token. So maybe, just maybe, we can simply look at the row in the attention matrix that corresponds to the classification token. And here we have similarity scores, which are really relevant scores or important scores, which will score each token according to how much it influenced the classification. So maybe all we need to do is just look at this attention matrix in the row that corresponds to the classification token and take those scores as our ground truth, right? As our explainability scores. Why not, right? So as all good things in research, 2 papers are being published. One, attention is not an explanation, which goes into NUCCLE 2019. And then attention is not explanation, which gets accepted to EMNLP 2019. So really the research community is battling with the question, what are these attention weights? Are these an explanation? Because some models are self-explanatory, such as, decision trees, where you can really see each decision that the model makes. So are transformers self-explanatory? So in our research, we claim that the attention mechanism is indeed an explanation, but we need to take 2 limitations into account. The first limitation that we need to take into account is, as we said, there are many attention heads. So this attention matrix is doubled by the number of heads. Each head calculates its own similarity scores. So how do we aggregate those attention heads? It is unclear if all the attention heads have the same relevance to the classification. And the second thing is we're dealing with deep neural networks. So there isn't only one attention layer. There are many attention layers. And each attention layer mixes the tokens a bit more, okay? So in the first attention layer, token 1 gets information from token 2. And in the second layer, token 1 is no longer token 1. It is token 1 with information from token 2 and token 3 and token 4. So when we look at really deep layers, which are the layers that most influence the classification, it is unclear what those tokens actually represent and what their connection is to the original tokens in the input, because everything was mixed using the attention mechanism. So we need to solve these two issues. One is how do we aggregate over attention heads? And the second is how do we aggregate over attention layers? So those two questions are still open at this point out there. Do you have questions up until now? Because I'm going to go into ways of solving these two issues next. Okay, great. So before our works came out, there is another highly influential work in the field of transformer explainability, quantifying attention flow in transformers, which is published in ACL 2020. And what they do is they propose in the rollout method a really simple solution for both these issues. How do we aggregate overhead? We simply average the heads. How do we aggregate over layers? We do matrix multiplication with, the comment that we're adding the identity matrix because of the residual connections, but it's really, a technicality. So we do head aggregation using averaging and layer aggregation using matrix multiplication. Really, the two simplest solutions that you can think of, and sometimes simple is actually good, right? Sometimes simple solutions actually work really well. But as we show in our paper, the rollup method really doesn't work so well on a vision transformer. So if you look at the peacock image here, the heat map doesn't really correspond to the peacock. The fish, the heat map doesn't really correspond to the fish, and so on. So this is the first and very simple solution that is being proposed. They also propose another method called attention flow, but I'm not going to go into it in detail because it is inefficient and we were unable to run it on the entire data set that we used for our paper. Okay, so let's go into the first paper that we published, which is Transformer Interpretability Beyond Attention Visualization from CVPR 2021, so really a recent paper. What we're doing is we're saying, the assumptions made in the previous paper in rollout were simplistic but nice. We like them, so let's go with it and expand it a bit. So head aggregation is going to be done with two mechanisms. One is LRP, which is an existing explainability method based on deep Taylor decomposition, and gradients. So what we're going to do is we're going to propagate LRP throughout relevance, throughout the entire network, and then we'll have for each attention map a relevance map. This relevance map determines how much each similarity scores influences the output. But in order to average across the different heads, we're going to need another mechanism that is, maybe more sophisticated than simple averaging. So we weight each relevance matrix using the gradients. So you can think of it really as a weighted average of the heads, where the weights of the average are coming from the gradients. And gradients are, very widely used for explainability because they have a very intuitive meaning, and also they allow us to get class-specific representations. So we solve the head aggregation problem using LRP and gradients. And again, creating a weighted average of the heads where the weights come from the gradients. And really, we don't use the pure attention weights. We use the LRP relevance values. The reason that we use LRP relevance values is intuitively because we just narrowed down the entire network into simply the similarity scores of the attention mechanism, right? There are other layers, there are activations, linear layers, there is, other than similarity scores, you have also the multiplication with the values matrix. So it is really limiting to look simply just at this multiplication between queries and keys. So LRP allows us to account for all the other layers other than the similarity scores that are calculated here. And as I said, the gradients enable class-specific signals. Layer aggregation is done similarly to rollout using matrix multiplication. Okay.
There was a question.
Yeah,
gradients with respect to what?
With respect to the output, to the logic of the output class. Say the model classified the image as a cat, then we create a one-hot vector where we have a 1 for the logit of the cat and zeros for all the other logits of the other classes, and then we propagate the gradients all the way back in the network from that output. Hopefully that answers the questions. So thank you, good question. So when we say class-specific signals, we mean that for images that contain multiple objects and you know, sometimes, usually even, it is more than one object in an image, we are able to propagate using the gradients a relevance map for each of the classes in the input image. So say here we have an image of a dog and a cat, we can propagate the gradients with respect to the dog class and get the pixels that correspond to the dog, and with respect to the cat class and get the pixels that correspond to the cat. Same here with an elephant and a zebra. So really our method, yeah, sure.
How do you measure the quality of the explainability method?
Okay, that's a great question. There are several ways to evaluate explainability, but I personally believe most in perturbation tests. Perturbation tests mean that, say, I claim that these pixels are the most important pixels to classifying a dog. Let's gradually take out or black out the pixels that I claim are important to the classification. If my pixels are indeed the ones that are important to the classifications, when I black them out, the model will have, you know, a very low accuracy. So we take a data set, we produce the explainability maps, we hide the tokens that our explainability method says are important, and then we get, you know, a very sharp decrease in the model's performance, since we really blacked out the important pixels. And this is positive perturbation, and negative perturbation is taking out the pixels that our method says are not important. So if the pixels that we claim are not important are indeed unimportant, the classification quality of the model will not decrease. So these are perturbation tests, but yeah, I hope that the idea is clear.
And there's also a comparison to just randomly removing pixels?
You can use it as a baseline, but really you have, you know, all the baselines here. So you compare your method to other methods, and in comparison, you really see the difference between taking out pixels that are really not important to the classification and taking out pixels that are crucial to the classification. Okay, so let's see some usages beyond those plain usages that we just saw. The first usage that I really like is detection of diseases. So when you use a network to detect a disease in, say, an X-ray image of someone's lungs, you can see here that the explainability explains to us why the model classified the top image as having bacterial infection and the lower image as having COVID infection. Really, the explainability tells us how the model identified each disease in the X-ray. So this is really cool to see, I think. The middle use is for detection of expressions. So the siding here uses a transformer in order to detect expressions in an input image. So you can see that really the model focuses usually on the eyes or the mouth of the person in order to detect the emotion in the image. And one of my all-time favorites is facial recognition anti-spoofing. This network is really explored on adversarial examples. We all use facial recognitions, on our iPhones or whatever, and we really want to know that someone can just print out a mask of my face and wear it and open my iPhone as me using a paper mask of my face. So really what we're doing here is we're showing all kinds of adversarial examples to show that the model is persistent to some, adversaries trying to hack our phone or trying to break the facial recognition model. So here you can see an adversarial example with heavy makeup, and the model detects the heavy makeup, a tattoo, which is detected as well, and a paper mask, which is also, detected quite nicely by the model. I think that the author of this paper, I saw him here, Neil. This is a use of our explainability that I really liked. It is semantic segmentation in the wild. If we do semantic segmentation, with Coco, say, our semantic segmentation is very limited to what classes exist in Coco. So say if we want to do semantic segmentation for other classes such as E.T. here or Mummy or the flying car from Harry Potter, we really can't rely much on models that weren't trained for, those specific classes. So what they did here is they use explainability maps for a clip, if I remember correctly, in order to create semantic segmentation of objects in the wild. So this is another nice use of explainability, which I think is, more original than just showing heat maps. Okay, so take two. CVPR did self-attention, but as we saw, our CVPR paper did self-attention, but as we saw, transformers have other attention mechanisms, such as co-attention and encoder-decoder attention. So our ICCV papers does head aggregation using only the gradients and dumps the LRP since it is computationally expensive, and layer aggregation by matrix multiplication, and does a simple expansion of our CVPR method to all kinds of attention, so also cross-attention and encoder-decoder attention.
So what is it? What is it? Cross-attention?
Cross-attention is taking the keys and the queries from one domain and the values from another. Yeah, and the values from another
so
domain.
WK, and WQ will be the same?
You can think about it as integrating information from two modalities in a single attention mechanism. So if we have both an image and a text, and we want to incorporate data from the text in the image embedding, we'll take an attention layer where the keys and the queries are from one modality and the values are from another. So we're actually adding information from the other modality into. This is actually also very similar to what we do for encoder-decoder attention. But this is something that we really didn't focus on in this lecture, so I invite you to further explore. So the first thing that we used our new explainability method for is CLIP, as I said, which is a model for matching images and text. So the model basically gets an image and text query and outputs a similarity score. How much is the image corresponding to the text? So if we have here the input image of an elephant and a zebra, what we really wanted to do is to see if the pixels that are highlighted for the text correspond to, the actual text meaning. So for the same image, the model gets the input an elephant, and actually the pixels correspond to the elephant. When the model gets the input a zebra, the pixels correspond to the zebra, and when it gets a lake, the pixels correspond to the lake. So the model really knows how to find the pixels in the image that correspond to the specific text, even though the image is the same image across all these experiments. So this is really cool, I think. Another thing we did is actually very similar to what we saw previously with the semantic segmentation, is we took a model that was only trained for object detection, and we used its heat maps, its explainability heat maps, as semantic segmentation. And as you can see here, with this example of the remotes and the cats, the explainability for the detection actually quite nicely corresponds to the semantic segmentation that we would expect for each one of the objects. The last thing that I wanted to show here that we used for our second paper is a VQA model. Any of you who work on NLP know that VQA is a tricky task because the task is giving a model a question and an image, and the model needs to answer the question according to the image. So here the question is, did he catch the ball? And we actually see a person catching a ball in a baseball mitt. So the answer is yes, but if you have explored these models, you know that sometimes you can black out the entire image and the model is still 40% accurate, which is quite remarkable. This means that the model can guess the answer to the question based on the text only, and sometimes not even refer to the image that it's supposed to, answer the question for.
Are those open questions or just yes or no questions?
No, it has, the task has a fixed amount of answers that it can answer. It's really a classification task. You have questions that are yes, no, black, white, car, plane, and other,
Yeah, so accuracy won't be the right metric to measure that?
Maybe that's a question for other researchers who do VQA and ask what is the optimal metric to evaluate VQA. But from my experiment, you can usually black out the entire image and still get pretty high accuracy. So explainability is really important here to understanding if the model actually looked at the correct parts of the image when it classified the answer. So here we see, for example, that the question, the model is Alex Mert, by the way, and the question is, did he catch the ball? The answer is yes, and the model actually really focuses on the relevant part of the image, which is the hand of the player catching the ball. I see that we have a question.
Yeah, I just wanted to ask if you think, I mean, you've showed here like a lot of different ways that attention explains the way models predict answers or work. But they were all, you said at the start you were going to focus on image processing. So do you think that this is easily duplicated in any field if you use an attention layer? Because it's not I mean, you can use attention layers not just in NLP.
Yeah, I totally get what you're saying. But as I said before, the reason that we use NLP was to avoid focusing only on the attention layers. So I think that if you have a model that has, a complex architecture and an attention layer, then probably it would be a guessing game to know if that attention layer can produce explainability for your model. Because sometimes really rollout even or pure attention weights, just taking the raw attention weights can produce great explainability, but it is unpredictable in the sense that it is unclear what the attention values themselves represent without, further processing. This is why we use LRP, gradients, methods that are common to explainability literature and not just pure attention weights. I hope that answers the question.
It does, but you could, so you're saying like specifically for your problem, you'd have to explore how to use explainability methods to incorporate with your attention layer. Okay.
Yeah, definitely. And I think that this is also the reason why, we try to take simple methods from explainability literature that worked quite well for convolutional neural networks such as LRP and maybe even LRP on the last attention layer and maybe GradCam, but they didn't produce quite the same results as they did for convolutional neural networks. So I think really explainability is quite more difficult, and it is a science that is quite more profound than what it is usually perceived as, because you really need to understand how your model works. You really need to have a strong intuition of what the model does in order to explain it and be able to produce something that is reasonable for it, in my opinion.
Thanks. Yeah.
Hila, so I have another question.
Yeah, sure.
So do you think this is easily transferable to other modalities?
Yeah.
Because in this sense, it seems that, if the architecture is like similar, it should work, right? Regardless of modality.
Yeah, definitely. It's something that should work for other modalities. And, I've neglected to show it here, but we actually have experiments on NLP and on text, and I know, and I've seen papers using our method on text, and it should, be able to make that transfer between domains, between data, between, it shouldn't be, sensitive to the modality that you use. But I will say that it is something interesting that I have seen using our explainability method, that sometimes, we said we do matrix multiplication across all the layers. Sometimes it is beneficial to clamp the back propagation until, not the first attention layer, but some intermediate attention layer. This is some kind of a hyperparameter that needs to be tuned. This is, an open question for me. Why can't you really propagate all the way back to the first layer? But it is something that, if you speak of sensitivity of this method, I think the biggest sensitivity of this method is that sometimes you need to clamp the matrix multiplication and not go all the way back, but go some way back. And it is something that I haven't been able to, see a consistent rule of how back you need to go. Sometimes you need to go all the way back. Sometimes you need, only the last layer is enough. Yeah, so this is still an open question for me.
Was that related somehow to the modality, or is it like modality?
No, it's modality insensitive. It's modality agnostic. It happened both in vision and in NLP.
I see. That's very interesting. I mean, some people claim that deeper layers have more, they are semantically richer.
Yeah,
right?
yeah, that's definitely true in our case too. Yeah, we have ablation tests using our method only on the last layer, and usually it produces very similar results to going all the way back, but still not quite the same. And for some models, you need to take only the last layer. For some models, you need to go all the way back. But basically, it is domain agnostic. Let's call it like that. And I'm not really sure yet what is the real reason causing this thing, because I have seen it, by the way, for clip with V-base 16 versus clip-base 32, where for clip-base 32, you can go all the way back with the propagation, and for 16, 16 by 16 patches, you need to take only the last layer, and people have actually commented that on our GitHub page, and they were absolutely correct. So even, the same modality with the same data can differ when you use as simple as, a different patch size. So this is really an interesting phenomenon that I'm not really sure yet where it stems from, but yeah, definitely something that I saw, and an interesting question. So thank you for that.
Great, thank you so much.
Any other questions? Okay, so I'm actually done. Thank you for listening. It was kind of hard not seeing you, but I hope you enjoyed the language, the lecture, and produced some new information from it. And it was great to be here. And thank you, Moshe, and thank you, Yonit, for inviting me. And it was great to be here.
You're getting a lot of claps, as you can see.
Thank you.
I think I have, if that's the end, I have one more question, if we still have time.
Yeah, sure.
Yes. Okay. So well, first of all, I didn't know that it's the end of presentation. So what I would like to say is thank you for the presentation. It was really great, very interesting presentation. I will definitely check your papers. Some of them I knew before, but not all of them. My question would be regarding causality. So explainability, as you said in the introduction, is something that we use, or we are trying to use, especially in the domains where we have where our predictions or our recommendations might have critical impact on something, maybe someone's health, maybe someone's finance, and so on. And last years we've seen like a very, very quick development of interpretability methods all over the machine learning field. Though still we know that explainability is not necessarily something that can inform us about the causal structure of the problem, right? So explainability might still leverage things that are related to correlations that are not causal. What are your thoughts about this here? In case of pictures, images, it seems that maybe it's a little bit different. In case of natural language processing, it might be maybe more complex. I was just very curious, like, what are your thoughts on this in general?
Yeah, definitely, and I hope this answers your question. I think the way that we view explainability now is quite flat, right? Quite shallow. We get heat maps, but we don't really know why those pixels, say, even in the image, were highlighted. It is possible that some pixels were highlighted due to their proximity to other pixels, right? We don't have that notion of knowing why, in a very profound way, each pixel was highlighted, right? Mm-hmm. So this is really an interesting question, because our method isn't able to produce those answers. So really, I think that explainability needs to, or will, in the next years, do an upgrade to, really exploring a more profound explainability than, just heat maps, which is nice and really useful in many cases, as we saw, not just to instill trust in users, but it is, as you say, quite a flat way of viewing explainability, and we don't really have a deep notion of what the heat map means in a deeper level. Yeah, so I definitely agree. If that answers your question, so I really think that it is something that we're trying to work on, that we're researching more profound explanations and a more profound notion of explainability.
Yeah, sure. Thank you. It was an open question, so of course it answers my question. Thank you so much.
Thank you.
Great, thank you all for joining. We're a bit out of time, so we lost a few people, but thanks a lot. Thank you for a great talk, Hila. We usually give a small gift for the people that come and
oh wow, thank you.
We gave you something.
Thank you very much. Very nice of you.
So bye all, thank you.
Bye all, thank you. Thank you very much.